Okay, welcome to Steve's version of stability at high transonic speeds. Okay, what we're not going to cover in this video is the definition of critical Mach. We're not going to cover the definition of transonic. We're not going to start from scratch with shockwave propagation and how shockwaves are formed. Okay, that was done in class for my current students. I will quickly recap how a shockwave is formed. Okay, and then we're going to cover these 5 points here, and we're going to try and do this. So this is meant to be in addition to the stuff I've done in the classroom, and it's just to help the students along when they come to prepare assignment number 3 for unit 48. Okay, this bit isn't the first part of the assignment. It's quite a big assignment. This is just the point that really covers the M5 criteria. Okay, and a little bit of the D1. Right, it's not D1, D3. Sorry. Okay, you've got your wing, you've got your standard aerofoil sitting like that. Right. Okay, and then what we'll have is we'll have some airflow over it. That air will be accelerated at the first part of it, right, over that bump, over that camber. Yeah, the camber on the top surface of the wing, because you've got the atmospheric pressure pressing down and you've got airflow, and it's being kind of, you have like on a wing you have kind of this going on where you have a convergent and a divergent duct. The other half of the Venturi tube is kind of, but the Venturi effect is caused by the atmospheric pressure pressing on all sides of the wing, presses on the bottom as well as the top. Okay, and that atmospheric pressure causes, like, you know, in between the atmospheric pressure and the wing trying to shove the air out of the way, it constricts it. Now at subsonic speeds it constricts the air. Constricts means squeezes without compressing in subsonic theory. Now we're moving to supersonic theory. That means when we squeeze the air, okay, we accelerate the air. We know that from Venturi's theorem, sorry. When we squeeze the air, it accelerates and goes faster. So we've got faster air, it's going faster and faster and faster. When it reaches a finite speed, the local speed of sound, which we've covered in our early studies, how to work that out. Okay, for people that can't remember, I think it's 20.05 times the square root of the temperature in Kelvin. Right? That's how you work out and that'll give you the speed of sound in meters per second. Anyway, forget the maths for now. We'll talk about stability and stuff. So, bang, it goes really, really fast. Yeah, the air is accelerated. The air accelerates to the point where the air cannot go any faster, right? Because what happens is the air particles at the front start to move at the speed of sound. The air particles behind it start to catch them up because they can't accelerate out of the way of them. Air can only move at that finite speed. Air particles of air can only move out of the way of an object at the speed of sound. Okay? If the object moves too quickly, it pushes them out of the way, right? And then they start to build up into a shock wave. And how the shock wave builds up is this air particle A is going as fast as it can. Air particle B catches up with it, shoves on the back of it, yeah, pushes against it. Right, we want to go supersonic as well. I'm going supersonic, I'm going as fast as I can. The air, sorry, not supersonic, they're going at sonic velocity. So the air particles are being accelerated over the wing. They cannot move any faster, so they form a shock wave. Right? They collide together and they start to compress. And this is what we talk about, the compressibility of flow. Now, again, this is the very basic Fisher-Price version. Any real aerodynamicists out there will sit there and go, it's much more complicated than that. And yeah, I know it is, right? But we're trying to make it level 3. Yeah. So you end up with a shock wave, that sort of shape there, and that's a lot bigger than the shock wave would actually appear on the aerofoil, but that's just so it shows a little bit better. Why is it that shape? If we remember our old friend the velocity gradient, okay, so the velocity gradient, the air that is being slowed down, this air here is trying to move at, as well as trying to accelerate, it's also slowed down by the surface of the wing. Okay, and what you find is, depending on how shiny the wing is, right, and depending on the velocity of and how much that slows it down, and lots of other factors, you can get some shock waves are this sort of, you know, you get that sort of shape there. Okay, so it forms a shock wave. Right, now the problem with that is, as well as the shockwave forming, at the back of the wing we have separated flow. And that's the flow. We're asking the airflow to change direction. Now when we ask the airflow to change direction here, we get the Coanda effect over here. The air will stick to the wing, okay, up to a certain point. If we increase the angle of attack and change the angle and we ask it to change direction too much, there will be too much energy in the airflow and it will rip away, the layers will rip away. You'll get what you call an adverse pressure gradient, okay? And then, so there's a little favourable pressure gradient there. If you get separated flow, you get what you call an adverse pressure gradient. Draw that properly. A gradient like that. And what that is the bottom layer, the top layer is basically overtaking the bottom layer and becoming turbulent. Okay? So if we increase the angle of attack, like that, we'll find out that we'll get separated flow at the back end of the wing where the angle becomes too great. It overcomes the dynamic viscosity bonds in between the particles of air, and the air becomes to separate away and become turbulent. Now that happens with increased angle of attack. We covered that before in the stall. Okay, why a wing stalls. We can come across a thing called a shock stall. Right, now a shock stall, right, now we'll do that in a minute. The first thing we got is standard separated flow, which isn't a shock stall, but it's similar to air becoming separated just because you're going too fast. What happens is, go faster and faster and faster, the air will start to become turbulent at the very trailing edge, at the very back of there. You'll start to get a little bit of turbulent flow, and as you go faster, that more and more of the air, you're asking it to change direction, and the force of the air going this way in the airflow, the air sitting there going, no, I want to go that way, I want to go straight on, or remain stuck to the wing. The faster you go, the harder it is for the air to stick to the wing. So as it gets ripped away, right, it becomes turbulent, okay? And here you'll have a little bit of transitional flow where it starts to wave a little bit. It's laminar along here, it becomes transitional and then turbulent. Some people call this the transition point, some people call it the separated point, okay, or the separation point. Okay? Transitional point, separation point. Whoever's marking your sign should accept either of those. They're both correct enough. Okay, right. So separation point or the transition point is where the air becomes turbulent. As that creeps up towards there, and as this shockwave gets a little bit bigger, we'll make it a slightly bigger shockwave on a standard subsonic cambered aerofoil on something like a jet provost or something like that. If you're trying to stick that through the sound barrier, you've got a very cambered part of the wing because that creates lift. Something like a glider wing, if you try to stick that through the sound barrier or up to about Mach 0.7, you'd find out you get a big shockwave formed on it, okay? Because it's not that bump there. The shockwave will form, it won't form at the front, it will form around about here, right? It'll form at the point of maximum camber of the wing. That was where the air was being accelerated. Now remember, when the air is getting accelerated, this is the starting point of the race, the leading edge. It starts to be accelerated, it reaches its maximum speed at some point near the maximum curve. Okay, so the shockwave forms at that maximum curve point and kind of hangs around there, right? What you've essentially created is you've created a little cone or a little a point of compressed air that is now attached to the wing. It's stuck to the wing and it is moving along with the wing. Now people think that the air has to flow above the shockwave and all that. Air can flow in and out of a shockwave, but the shockwave will slow it down while it's compressing it. So it acts basically like an air brake. Okay. So what happens is, or a spoiler if you want to call it that, right? But it sticks up there. Now underneath it, remember, where the shockwave is here, underneath this part here, right? In order to have lift on a wing, we need to have a difference in velocity above and below the wing. And that creates a difference in pressure above and below the wing. If our air is stagnated, if it's not moving, right? If that air is in that shockwave and it isn't moving, it is not creating a low pressure area. So here, it's not creating low pressure, it's actually pushing down the wing, creating high pressure. And what essentially it does is, for that part there, that hatched part there, it turns off the lift at that part of the wing. That part of the wing is no longer producing lift. as well as that, separated flow. In order to produce lift, we need laminar flow. Only laminar flow really. Turbulent flow and transitional flow and vortex flow can produce some lift, but only laminar flow is really producing lift. So if we've got non-laminar flow in the blue section there, we've got no lift. Now because this air is moving a lot faster, it's been accelerated over the bump, over the curve, right? It's moving faster. It is moving at the speed of sound. It is momentarily, until it forms a shock wave. This is supersonic flow, right? The wing is moving faster than the speed, or the air is being accelerated over the wing, and it's moving faster than the air around it. It's moving faster than the air underneath it. So you do get a kind of like super lift effect at the front. You get a slight increase in lift at the front. But what mainly happens is, towards the rear edge, if you then take your centre of pressure, so if you take your, you know, we had a pressure grade, I think we had a pressure map or something, or a pressure gradient over the wing like that, and then we drew these lines on it, you know, and this is the pressure pressure in normal subsonic flow. You have this kind of pressure around the wing. It won't look like that. It'll probably be, it's more of a bump like that really, yeah, and you have, that's how the pressure's dissipated around the wing. That's where your lift is, okay? It's your bubble of lift. That's the difference in pressure above and below the wing. That difference in pressure is sucking the wing into the air, according to Bernoulli's theorem. Right, now, when you've got that, your centre of pressure, okay, might have been here. Now, your centre of pressure, because you've lost some lift at the back end, and in extreme variations you can have turbulent flow all the way to the back. The turbulent flow at the back will, as you go faster and faster and faster, will increase until it meets the shock wave. Okay, and then the shock wave kind of sweeps the wing and takes the turbulent flow back over. Right? So as the shock wave moves further back, as you go faster and faster and faster, the shock wave will form further back on the wing until the shock wave forms at the trailing edge. So this is like about Mach 0.8. Okay, once you get to Mach 0.95, you get to this sort of effect here, where you have a shock wave, and the shock wave can get smaller, and sometimes it'll angle back a little bit. Generally, a normal shock wave, you have a normal and oblique shock wave. A normal shock wave, as found on a wing, will be 90 degrees or perpendicular to the relevant airflow. Okay, so I've drawn that wrong. It wouldn't sit like that. It'll sit like that. Okay, and you might find the shock wave gets slightly smaller as it goes further back, and then your separated flow, right? A weird thing happens that when you start going faster and faster, this supersonic airflow over here where it was becoming turbulent, right, because the force on it, it was moving too fast to stick to the wing to change direction. When it goes supersonic, it sticks to the wing in front of the shock wave a little better. Well, it kind of, it'll only go to a certain point there, so the back end of the wing, once it's gone to this part here, right, as the shock wave comes back, you sometimes get, when you get Sheila in photography, you sometimes get this, where you have a shock wave, right, and you have, at the bottom, you have this kind of effect there, where the shock wave starts at the transition point, and then you get turbulent flow underneath it and a shock wave above it. Okay, but the main thing is, at this point here, if you get this turbulent flow all the way up, the whole back surface of the wing is no longer producing lift. Okay, and the front surface of the wing, the centre of pressure, instead of being there, is now between these 2 points, and your centre of pressure has moved there, it's moved forwards. Now, depending on your balance of your aeroplane, this can have all sorts of effects. Okay, so that's why the centre of pressure moves, because the shock wave, and the other thing that will happen that I've missed off a little bit will be, if you've got a standard airfoil like that, you get a shock wave at the bottom. You'll also get a shock wave that might form about there, because that's curved as well, right? And this will move back slowly, and this, because it's flatter, which becomes more important with the area rule and with sweep back and things like that, because this hasn't got a bump to stick on, hasn't got a cambered part, anything cambered on the aircraft, a shock wave will form on it, and then the shock wave will kind of, it doesn't stick to it, you know, saying that it sticks to it means that it, you know, that you're on about viscosity and things, but basically as you're going faster, the shock wave will stay in that place on that bump. Okay, and if it's to do with the cross-sectional area and how it's to do with how the wing coming through the air is displacing the air molecules. So we'll get stuck there a little bit. If we just say that for now, right? Again, get stuck on the bump. Because it's flatter here, the bottom shock wave will be smaller because there's not as much camber, right? And it will not get stuck on the bump. It'll move back faster. So if this is Mach 0.78, yeah, at Mach 0.8, this one's probably overtaken that shock wave. Yeah, and then if you go to Mach 0.9, shock wave might be there, and then the back shock wave might be there, and then if we go to during the airfoil there, and if we go to Mach 1, you'll find that both shock waves have angled back slightly and become a kind of trailing shock wave attached to the very trailing edge of the wing. Okay? Right. While all that's happening, when there's a shock wave there, there's no lift under a shock wave. Okay, there's no lift under a shock wave, and there's no lift under separated flow. Right? That means the centre of pressure is generally moved forwards. Depending on your balance of your aeroplane, if your centre of pressure moves forwards, right, the way, if you think back a couple of lessons ago, we had this going on, so we'll make it a little aeroplane like that. Okay, and we've got and we said that we had thrust and drag generally happens a bit further up. You've got thrust, you've got drag, you've got lift at the centre of pressure, C of P, and then you've got your centre of gravity, your C of G, right, and you've got weight there, and generally most aircraft have the centre of gravity forward of the centre of lift or the centre of pressure, and then the balance, right, either if you have an aircraft that's perfectly balanced and doesn't have a lot of tail trim on it, right, you'll have the thrust and the drag. The drag will be higher than the thrust. With a lower wing, a lot of the drag's created by the wing, so the drag might actually be in line with the thrust. If that happens, you'll have a tail, okay, and you'll have a bit of downforce on the tail, right. That's just exactly the same lift. It's an upside down airfoil, it's creating lift in that direction instead of that direction. You'll have the lift lifting it up, and because it would be nose heavy, you'll have the tail pushing it down with a bit of negative angle of attack on the tail to balance that out. Okay, to make the aircraft fly in a straight line. And that's your force couple. Okay, you can, because you have a nose, the lift and weight will make a nose down force couple, and thrust and drag. If you have your drag high up, okay, so if it's a delta aircraft, how you balance that out? If we make a delta aircraft, you won't have any downforce at the tail, right? The delta aircraft will have to have the drag higher up, okay, and then the thrust and drag will make a nose up couple, which will cancel out the nose down couple of the lift and weight. Right, that's going back, that's a recap back into stability. How does this affect our shock wave? Right, so now Sammy's shock wave comes along, right, drawing it massive there, knackers up our lift, and our lift now moves forward to there. Now we don't have as much of a nose down couple, yeah, okay, so that's that nose down couple. Now there's not as much leverage with that, and you'll find that the nose will come up a little bit. Right, okay, got that? So that lifts the nose. So when the shock wave moves forward, the nose of the aircraft is going to lift up a little bit. Okay, right, now let's look at what's happening on the wing. The nose of the aircraft is lifted. I only have currently kicking about, I don't know any model jets kicking about. Model jet phase? Oh yes, I do, we'll have a Typhoon. I'll just get that, 2 seconds. Okay, so now we have a model jet there, and what's happening is, it's flying along like that, yeah. You've created a shock wave in the centre of the wing. The shock wave has moved, the shock wave has dumped some lift and moved the centre of pressure forwards, which is going to raise the nose slightly, ever so slightly. As the nose raises, the angle of attack is increased. As the angle of attack is increased, right, we're going to create more drag. It's going to slow the aeroplane down slightly. As it slows the aeroplane down, yeah, what happens is the shock wave which was created by the aircraft speeding up and approaching Mach 0.7 or Mach 0.8, whatever the critical Mach is. The critical Mach number will change for different wing styles, different aircraft, and it will also change for different atmospheric conditions and pressures and densities and things like that. But generally, critical Mach, the pilot will have a critical Mach for their aircraft, and they'll know if it's a subsonic aircraft not to go near that because that's dangerous. Okay, so shockwave forms on the wing, nose comes up, slows the airplane down slightly. When the airplane slows down, there's less airflow going over the wing, so the shockwave will disappear, right? Which will allow the nose to come back to its normal trimmed flight. So what you have is, you have this sort of oscillation here. Shockwave forms, aircraft slows down, shockwave goes away. Shockwave forms, aircraft slows down, shockwave goes away. Now, if that was nice and gentle, and you're trying to, oh, you know, got a bit of a shockwave here, which can happen on some aircraft when the way it's designed, but the very first supersonic aircraft were not designed, they hadn't worked all this out yet. They knew something was going to happen, but the things like the de Havilland Swallow, right, with Geoffrey de Havilland on board, which was an early Delta aircraft, like a mini Vulcan, basically at critical Mach, it suffered a violent oscillation. This sort of shockwave appearing and disappearing, right, onto the trim of the aircraft, so you had that going on. Okay, 2 pilots flew, 1 died, 1 survived. Geoffrey de Havilland Jr., which was Geoffrey de Havilland's son, was quite a tall fellow, and in his book, Eric Winkle Brown, personal hero of mine, Eric Brown, he was quite a short fellow, and he said that maybe the reason that de Havilland wasn't able to recover from the oscillation was because he had his head and neck would have been further up from the straps in the ejection seat, and the backwards and forwards motion might have actually broke his neck. I don't think anybody really knows. But he went, very brave man, went to go and test flight, the first British people to try and get through the sound barrier, and was tragically killed. Eric Brown flew the same aircraft, and he suffered the same oscillations, but because he was a bit shorter than where his helmet was next to the paddle in the ejection seat, when that sort of happened, he was able to wrestle control of the aircraft back and landed the aeroplane, decelerated away from the sound barrier. These brave people are the reason you can go on holiday today on an A380 at nearly Mach 0.9 in safety, because they did all the pioneering work without computerized simulations. You know, strap your bum to it, go and hit the wide blue yonder and see how it flies. You know, brave people. Right. So that oscillation that we can get at critical Mach is dangerous. Yeah. If our aircraft is not designed to go at that speed, at Mach 0.9 or Mach 0.95, and you get this oscillation going on, that's not what you want to happen. Caused by a large, powerful shock wave destroying lift at a critical point of balance of the aircraft. Right, hopefully that's explained that. So that's the problem that we're trying to solve, or one of them. The other problem that we're trying to solve is separated flow. Now, first way we do that is separated flow. The other thing with separated flow is, so your Spitfire, right, in a dive, if you look where the wing is, I'll show that up with the camera, right, if you look where the wing on the Spitfire is and look where the tail's quite low down, you know, it's above the wing. People had worked out already that the turbulent flow on the back of the wing, when the aircraft was stalling and things like that, you need to have the tail higher so that the elevators didn't suffer from the turbulent flow coming off the back of the wing. What they found with Spitfires diving to try and intercept V1 flying bombs was, when the aircraft was in a dive and it was approaching the speed of sound, the turbulent flow off the back of the wing was actually a big cone, right, which was affecting the tail, and the tail itself, the tail plane itself, was creating, you had separated flow in the tail. Okay, so how they got rid of that? I thought, right, well, you know, I'll give you a clue. If you get rid of the tail and have a delta configuration, yeah, you don't have to worry about separated flow affecting the tail and buffeting the tail. Right, I'll just draw that for you, so you know what I mean by that. So if you just look on the model there, if we put a tail down at sort of Spitfire level, put a tail plane down there, got this cone of turbulent flow off the back of the wing, and if it hits that, it causes buffeting on the tail, and it could actually take the lift away from the tail, which means you haven't got your downforce anymore. So when that separated flow gets so bad, it destroys the lift on the tail, or upsets the lift on the tail, which upsets the balance of the aircraft, which makes it go nose down. Okay, what some Spitfire pilots reported was, when that happened, was they got stuck without the downforce on the tail in a nose down death dive, yeah, that they could not pull out of, because when they pulled back on the elevator was in separated flow. So a control surface in separated flow will not work. Yeah, which brings us to ring fences and things like that, and vortex generators. Right, so how to get rid of that is you get rid of the tail plane. Yeah. So we'll just do delta wings for the first part thing. So delta wing, your cockpit at the front there, you've got your transonic aircraft, okay, air intake, delta wing, so you don't have a tail, you have just a fin, okay, and then any separated flow from the airflow is coming off here. Yeah, it's still destroying lift, it's still affecting balance and things like that, but what it's not doing is ruining your control effectiveness, because basically your delta wing it's not interfering with the tail, because there's no tail to interfere with. That's only half the problem. Okay, right, your delta wing has still got a lack of control effectiveness. From our previous lessons we'll know that the delta wing won't be fitted with ailerons and elevators, it will be fitted with elevons. Okay, now those elevons, I'm going to draw them in red, will be back here. Yeah, and I'll just zoom that in a bit. So with your standard control surfaces, there's your delta wing, okay, and the back section here, it's got your elevons. Now, problem with that, couple of little problems with that is, when the shock wave comes all the way back to here and covers part of here, and the separated flow covers the elevons, you've lost control in pitch. Okay, so there's various ways around that. Concorde, for example, you have a crescent wing, which is kind of like that sort of shape. No, sorry, it's not. Sorry, canted delta, not crescent wing. Crescent wing is that sort of shape. So the Typhoon, if you see that one, if you look along the wing from there, that looks like a straight delta. If you look very closely to a real one, you'll see that it actually is a slight crescent shape, and it changes towards the edge of the wing. There's various reasons for that. It gives it more lift at low speed, and there's all sorts of stuff like that. Forget crescent wings for now. But basically the crank delta on Concorde, it forms vortices like that, like a triangle of vortices like that. Okay, and it makes that sure that the elevons, yeah, and the flaps, so I think Concorde has standard flaps, not inboard elevons. So the elevons, right, the way the shock wave forms on a swept back wing for a Concorde is that the shock wave will form along that wing like that, and it will never cover all of the elevon. Yeah, I've drawn that look too low. Can you see that on there? Well, hang on. Yeah, I'm drawing bits on it you can't see that. It's beneath that, sorry. Should know that. Where's the bottom of the screen? Over there. Right, so, sorry, I'll just... So if you delta wing, you can arrange the delta wing so it here's your delta like that. And what you want is you want the shock wave to form along it. The shock wave won't form across it like that. The shock wave should form along it like that, and then you arrange it so that hopefully the shock wave will not form. You have to make sure that when you put your elevons on, that the shock wave doesn't cover all of the elevon as it moves back. Right, one way of doing it. Problem comes if you have swept back wings, okay, which are like that, and you have that's why you'll very rarely see a wing with the same sweep on the trailing edge and the leading edge. They generally have a more swept back leading edge than the trailing edge, so that when you come to control surfaces on the back of them, yeah, then the shock wave doesn't cover. If it's parallel to the leading edge, it doesn't cover all of them. There'll always be some parts of it that stick out. But there's other ways around that, which I'm going to talk about in a minute. So what you can do is, you can have a sawtooth leading edge. So if you put a sawtooth on the leading edge like that, right, now they're in various places on different aircraft, and what they do is, they create a vortex, or they create a kind of triangular vortex like that, which is some swirled air. Right? So if I had a sawtooth there, you would get this kind of vortex That will go that way. Now, a vortex, if you've got turbulent flow, which is chaotic, and you've got a vortex, which is swirling flow, but that swirling flow is controlled. Okay, so a vortex will still give you some lift, and if you put control surfaces into a vortex, the part of the vortex hitting the controller surface and deflecting off them will still have some control effectiveness. Okay, so vortices can be used to maintain control effectiveness. You can have a sawtooth leading edge. The other thing that you can do is you can have little blades, which you see on some aircraft. A good example of that is the Hawker Siddeley Harrier. These are all old aeroplanes, but the Harrier, the Gloucester Javelin has loads of them. Okay, and you can put them either along the leading edge like that, and the ones on the leading edge help to maintain laminar flow over the wing. They'll create vortices only at high angles of attack, yeah, and then they'll make sure that there's a vortex over the wing to stop it stops shockwaves forming where you don't want them forming, as well as that it maintains control effectiveness. You'll also see some of them have almost like a forest of vortex generators just in front of the trailing edge, in front of the control surfaces. And what they do is, where your control surface will be subjected to separated flow, they create a vortex, right? And that vortex over the control surface, that vortex flow is better than turbulent flow. It's not as good as laminar flow. There's always drawbacks in engineering. You can't have laminar flow, you might as well have vortex flow. Right. So we've done sawtooth leading edges, vortex generators, wing fences. Right, now that's in the BTEC kind of a wing fence. If I just go up my little wing there, right, just rub that off. We've got this thing called span-wise flow. I've talked about span-wise flow when we talked about induced drag. Okay, so if you have a wing like that, the Sukhoi Design Bureau in Russia was very, very keen on wing fences. So if you put a big massive fence on the wing, and the side view it would look like that, and you would have this big kind of fence sticking up. Okay, sometimes sometimes very small ones, sometimes big ones, but just a blade sticking up in the middle of the wing. And they sometimes do the same sort of thing, and they can create a vortex behind them, okay, or they can create a sort of flow behind them. But they're mainly there to stop span-wise flow. Right, and span-wise flow can be a problem because span-wise flow creates large vortices, right? Large vortexes at the wingtip. All the vortexes created by we should say what span-wise flow is. You've got the air going above the wing, which I'm going to draw in blue, is low pressure. It generally, and I'm exaggerating the flow here, it generally flows in towards the fuselage. Air going under the bottom surface of the wing is high pressure, okay, and that generally flows away from the fuselage. Now at the trailing edge, you'll see that high pressure and low pressure, the low pressure one over the top and the high pressure underneath, the change in direction caused by the pressure. So if I just draw the fuselage on there, if you imagine that being, there's the fuselage, there's the wing, right, okay, so low pressure air is wanting to suck in a little bit, so that's going that way. Yeah, and high pressure air underneath the air is what is hitting the fuselage and kind of being pushed out over. It's just the way it works. It's you know, I mean the high pressure air is actually going that way as well at some point, but that's going to cause interference drag. Okay, but it's going that way, and at the wing it will leak round. Okay, at the wing tip. That's why we get winglets. So winglets can be used to prevent that. It stops the high pressure air coming round, and the low pressure air stays where it is. Wing fences act the same as winglets. Before we had winglets, we had wing fences. Okay, and they're to just cut down on that span-wise flow a little bit. Yeah, so it stops it happening here. It won't allow the low pressure to go that way, and it forces it to go that way. Okay, and it also doesn't it straightens out there a bit. Right. Now what that does is it cuts down on the amount of vortices that you have on the back, on the trailing edge of the wing, and then what that will do is, so all the vortexes, when all of the air meets at the trailing edge, you get loads